Hello. Okay, this is the paper we're going to talk about. This will be fairly informal in the grand scheme of things. I have slides, but those slides are trying to prompt you to talk about things. If you haven't read the paper, that's fine. We will go over part of it ourselves. So, let's see if this works.
One thing out.
Yeah.
Questions during, questions after?
Questions during. Raise your hand if you have a question. I will repeat it so it's recorded as best we can do so.
Yeah. So speak loudly, those people in the room also hear you.
Yeah. So, paper. Oop. Who am I? I'm Alex Kesling. I worked at Google once upon a time. I've now co-founded a company called Empathic working on agentic AI access to enterprise data. If you're curious about that type of stuff, talk to me later. I won't talk about it again. Why this paper? Because I read this paper last year and dug a lot more into modern big data stuff and started actually recommending this paper to people when they started asking about database systems, because it does a really good job of just kind of giving an overview of what a modern database architecture kind of looks like and why you would structure it the way you do. And I thought it'd be kind of cool for a PapersWeLove talk. I will post slides that have more than this after the talk so that you can actually have some context without having to listen to me blather on the whole time. Don't worry too much about taking pictures. It'll be easy. So the structure of the talk. First, we'll talk about the paper for especially those people who have not actually read it. Then some minor navel gazing, followed by, quote, building a database. We'll see what that looks like later. So the paper. Show of hands, who has read the whole paper? All right, we have a couple people. Any of the paper? All right. Who opened the paper? Okay, a few people. Okay, we have some context. So let's take a moment to kind of look at this. I've been coming to these PapersWeLove for a long time now. How long has it been? A decade? A long fucking time. So I remember when there was a whiteboard involved, when most people had actually read the whole paper, and we're gonna go over a little bit just so you have some context here. So I like to start by just kind of reading kind of spiral from the outside in, seeing the big stuff first and then kind of focusing. And so let's start with just kind of the title and the abstract. And the first thing we see in the title is this big word Apache. And you might be familiar with some Apache projects, but Apache was founded in '99. And generally, it means a lot for something to be an Apache project. Not just that the source is open, but also that all of the development is done in the open, on open platforms, and all decisions are made in the open, which kind of implies a lot about the general structure of a project that is Apache. The next thing you'll see in that title is Apache Arrow, another Apache project. This is interesting. Is anyone here familiar with Apache Arrow? Raise your hand if you're familiar. Would anyone like to say one thing that's special about Apache Arrow? Someone? Anyone? All right.
Cross-language.
Cross-language. That's cool. Another thing. One more thing. Anyone?
Zero copy.
What?
Zero copy.
Zero copy. Cool. So let's talk about the zero copy thing for a moment. Generally, what we mean when we say zero copy is we actually mean that it's memory mappable. That when you share it across some interface boundary, say you have two servers that are talking to each other, and you share the data across it, you don't have to transform it multiple times like you do when you have a deserializable format. And that means that any time you can pack it reasonably so that it's sufficiently efficient to transfer across a memory boundary, you don't have to spend the cost of that serialization. Another really fun thing about Arrow specifically is that it is column-oriented. And what column-oriented kind of means is that all of the same data is stored together. So in a row-oriented structure, you can see the outlined blue boxes are effectively structures, and then they each have their own fields. And so it's efficient to read all of the fields on one structure together, but it's not efficient to read all of the separate values of the same field across them. Arrow makes it really efficient to run SIMD, simultaneous, or single instruction, multiple data, instructions across it. And so you can actually just run through a contiguous chunk of memory and efficiently do that. Those two things together make it really useful for data processing systems. In the title, it also talks about being fast. This is an interesting property for a system like this to call out explicitly, because doesn't everyone want their database systems to be fast? Why are you specifically calling that out? Embeddable? Are most query engines embeddable? In fact, one of the dynamics of this paper is it's referencing the fact that most query engines are not embeddable. They're built into vertically integrated systems that are not modular, that don't have pieces that you can reuse. Then it talks about analytic query engines. Here are a bunch of other examples of this, but really this is here to show there are a lot of other people in this space. Like, what is novel? Why is this a new published paper? Why is this a thing that people want to do if there's so many other things? And the last thing that's called out in the abstract is specifically this. At the end, DuckDB is called out very explicitly as one of these things to compare it to. And the reason why DuckDB is called out is because it is also an embeddable query engine. It also plays in this same space. And so a lot of the discussion of the DataFusion paper is directly in conversation with DuckDB. Next step of this is to think about the introduction and conclusion. And those really are best summarized by thinking about this logo. Does anyone recognize this? LLVM. This thing kind of changed how we approached compilers. And DataFusion, in large part, is trying to change database systems. It calls itself out multiple times in the paper as a comparable thing to LLVM. And that's a big claim. That's something that's a very interesting thing to talk about. So here's kind of my loose paraphrasing of the intro and conclusion. And because there are a lot of words, I'll just pause for a moment for you to kind of look at them. But the general claims in this are it's kind of LLVM for databases. It is loosely coupled, so it's reusable. And more particularly, all those databases we saw earlier are pretty vertically integrated and expensive to build. People keep building new databases. And that seems to be speeding up, not slowing down. So clearly there's something weird going on. And DataFusion is trying to be a better way to do this at scale. Like if you actually have novel data or novel context, instead of trying to build a completely new thing from scratch, what if you actually reused some components? Wouldn't that have some interesting implications? Most specifically, if everyone's building on the same core, couldn't that make everything better like LLVM? Like Kling is really the dominant C compiler now, not Microsoft Visual. Huh? GCC is dying, effectively. This is a claim from me. Don't treat this as truth. I claim that GCC is dying, but that's just me. So next thing I look at after the intro and conclusion is all the diagrams. Like these are the things that the authors thought they needed to highlight visually, the things that really differentiate it from other stuff. And there are lots of things here, so let's just simply summarize this. And you'll see DuckDB comes up a lot. Fundamentally, all of these diagrams showing performance are DataFusion versus DuckDB. And then the other ones are just kind of high-level bits. It's modular, it's parallel first, and it's generally useful, right? But DuckDB is an interesting thing. So why compare this to DuckDB? And really, like they're both embeddable systems, they're both fast, they're both about analytic queries, and they're both open source. But the big differentiator here is DuckDB is the vertically integrated GCC of the world in some ways, and DataFusion is the LLVM. It's the trying to be generally available and you can plug into all the pieces. And here's the abstract for DuckDB specifically, which to over-paraphrase is trying to be SQLite but for analytic workloads. And that's kind of an interesting thing. So, pause for questions. Any questions so far?
So what is the IR?
What is the IR?
Yeah.
We will get to that. The IR functionally is, what DataFusion calls a logical plan, and it represents all of the operations that occur during the query execution, but in an abstract context. In fact, we'll go through the distinction between the logical version of a plan and the physical version of a plan a little bit later. But it's a tree of operations. You can think of it as if you start with SQL and you parse it into the AST, the next thing you do is you take that AST and you generalize it into a logical plan. And you could separately use like IBIS or Pandas or whatever and construct a data frame like thing. But each of those ops on the data frame can equivalently be built into a logical plan.
So can Pandas, I guess, theoretically be converted to that logical plan? Like if I write Pandas code, can it be then?
Why, yes, it can. And in fact, IBIS, which is a much better API, as some people in the room might tell you, actually under the hood can use the DataFusion execution engine, and it does exactly that. Any other questions?
Am I a fool for not having heard of DuckDB before now?
No, but DuckDB is fun. I would recommend playing with it. It's at least smaller than DataFusion normally is. Though, if you want to do anything that requires extension, I would highly recommend using DataFusion because DuckDB's APIs are a little bit hairy at times. Anyone else? Cool.
How about Polars? It's an ISO player that's showing up.
Yeah, so Polars is interesting. Polars is much more vertically integrated. It's its own kind of core project. It solves some similar problems, but it doesn't as generically do it. And so like if you're especially talking in kind of the core data analysis space, it's cool. I think DataFusion is more generally useful for like database engineering and large scale systems because of how easy it is to extend and play with. We can talk more after if you're still, that didn't quite phrase things. Okay, so this is a pretty big bibliography. A lot of papers are much smaller. This calls out a whole lot of database infrastructure and tooling and general papers from the last 20 plus years. In many ways, one of the reasons why I've been recommending this paper for people to read is because it is a secret survey paper. It kind of like talks about all of these other things and how they relate and gives the architecture they decided on as a result of the unification of these. And in the paper, in the context of these databases, DataFusion calls itself out as a member of this class of deconstructed databases. Of instead of these things being vertically integrated and all there, what if we pulled all the parts apart so you can actually use them individually? So some brief navel gazing. We've used the term database a million times. Could I get 2 people to define a database for me? Tom.
Best way you put data and we get it out.
Some ways you can put data in and get it out again. Another definition.
Data management program.
Data management program. If I kept asking people, I would get a whole bunch of different answers. In fact, probably most of you have a slightly different version of what a database is, and yet we've talked about it a lot up to this point. So maybe we should take a moment to define a database. So what's a database? I have my own criteria of it, and since I'm talking, that criteria will be what we use for the rest of this talk. I call it the Kesling criteria. Here's the informal version of this. 1, you can ask questions of it. 2, it returns data. It's a database if you can ask questions of it and returns data. This is a very loose definition, and it's one that is like a little bit arguable, but I'm the one speaking. Here's a more formal version of this. A dynamically configurable query semantics, not a query language specifically, but a semantics, and a data retrieval system. And the reason why I phrase it this way is that you could imagine interfacing with a database using procedural language and imperative language like Python or SQL or whatever, but the semantics could be equivalent. And the data retrieval system is necessary because if you don't get data back out of it, how is it a database?
What do you mean dynamically configurable?
You should be able to, at query time, perform 2 different queries that you think of at that time and are not defined ahead of time with the database. The database shouldn't just have things pre-baked. For the purposes of this, that's not a database. That is a superset of a database. That is a mutable database. In this case, the minimum requirements for a database are just these things. And in this case, the data can be completely read-only. You can imagine a library of books and a librarian as the kind of dynamic here, where you have your data retrieval system that is the library of books that you can grab, and the query system is the librarian plus the card index before we had computers, right? Fundamentally, that still fulfills the requirements of a store of knowledge and a database that you can dynamically query, but you aren't mutating the books. It's still the same set of books, and you're just performing different queries over them. There are other things that you might associate with a database. There are many of them. This isn't even all of them. Write is just one of them. User management, access control, general resource management. You can imagine a like massive distributed database that has to deal with nodes dying all the time and like self-healing and all of these things. In my definition, these are not required. They are optional. Some example storage systems. Python dictionary counts in this case. It doesn't have to have a disk. It can be fairly simple. But just reading a key is not powerful enough in the general phrasing of a query system. You need to be able to actually have some new insight from something, not just get the thing back that was previously stored there. Now, there are dynamics around like range requests that could be useful, of like, tell me all things that are in some range is actually a meaningful query in my mind, because it can inform you about what data is stored there. But if you say just, is this individual value available, it is not yet at the level of database. A map is not a database.
So key value store is not.
A key value store is not a database. You can build a database on a key value store, but a key value store itself is not a database.
Okay, we'll go with these definitions.
I am the arbiter of this talk, and I say it goes. So that means we need a query semantics that is more than that. We need to think about kind of bits on top of that. Here are some example databases. You'll note I have effectively a storage system and a query semantics. And the first one on the list is the ext3 file system and the find command. Those together are a database in my definition. CSV and Pandas, SQLite itself, which is the SQLite format, and the SQLite bytecode engine that runs on top of that. SQLite is kind of an interesting example here because its like internal representation is actually a virtual machine that runs bytecode. Some other examples here of Postgres, Bigtable, and Dremel, aka BigQuery. Sit in this regard. Any?
Does like JSON with like a JSON library kind of count?
I think a JSON file plus JQ could count as a database in this regard. Anyone disagree?
So too bad.
All right. So now that we've navel-gazed for a minute, and we kind of have an idea of what this paper is about, let's build a database. I think it's kind of really necessary to understand this idea of it being modular and easy to build new systems with DataFusion, and I think it can be fun to do this. What we'll need in this case are data retrieval system and query semantics that have exploded to the kind of pieces loosely that DataFusion phrases these things as. And we'll go through each of these pieces to kind of build a core of this, and then we can expound on that. Starting with the storage engine. For my purposes for this demo, the Apple file system will be my storage engine. CSV files will be the storage format, because we can store tons of data that you might otherwise think of as being in a relational database engine just in CSV files. Doesn't have to be complicated. We're not trying to be the fastest thing in the room in terms of all of the fundamentals here, just demonstrate the shape of this. And fundamentally, this also kind of shows you can serve whatever you want with DataFusion. So the query semantics will be fulfilled by DataFusion, and we'll start from the top down. And I have some little code snippets here that kind of show the shape of this, but if you don't read Rust, that's okay. And we can kind of talk through what is happening. So DataFusion out of the box uses the SQL parser rs crate, but you can use whatever you want to parse SQL. Like SQL, you could do SQL glot in Python and then somehow transfer it to a substrate plan and then whatever. It doesn't really matter. The general idea here is that it's just parsing into a SQL abstract syntax tree. Fairly straightforward. The compiler is slightly more complex. It takes the set of statements from that abstract syntax tree, it looks up the table references and constructs some state around them, and then with those options, it builds a logical plan, which we mentioned earlier. So effectively what this does is it takes the abstract syntax tree and it creates a new tree. That new tree relates to the semantics of that abstract syntax tree of SQL, but it represents it in a way that DataFusion can operate on. The logical plan is really just an enum. It's a recursive enum that represents a tree. There are a lot of different types of operations that can be represented in the logical plan. This is just a slice of it. And you can build a logical plan directly. you don't have to think of this as just being generated from the SQL AST. You can use kind of a builder API to do each of these operations that are equivalent to SQL statements that you might otherwise write. From there, we have to figure out, like, okay, we have this abstract plan. We are selecting some field foo from a table bar. What does that mean? Like, I need to read bytes somewhere. We haven't even constrained how many rows there might be or all sorts of other dynamics. We're very dynamically figuring out what on earth is going on. We have to go from that very abstract phrasing of things into something much more concrete. And DataFusion represents this as a transformation from a logical plan to a set of execution plans.
Those types, the execution plan and the logical plan on the last page, those are DataFusion types, or are they types that you're creating?
They are DataFusion types. And in fact, you'll note a slight difference here. The logical plan is an enum, whereas the execution plan is a trait. A trait in Rust is functionally an interface. It is something that you can implement a version of. In the context of our CSV database, we are going to implement a CSV exec effectively. And it has this execute method on it. And what this method does is it effectively says, like, how large is this? What is my context? And it returns just a stream of record batches. Record batches are phrasings from the Apache Arrow project. A record batch is some set of rows that are structured as column-oriented. So you might have a million rows with the first column all contiguous in memory, and then the second column all contiguous in memory, et cetera. And that is one record batch. And in this case, we have some future in Rust that will return that record batch set. And we are structuring this so we return a reference to the stream.
Is the logical plan extensible or sealed?
The logical plan has, I believe, a custom entry that you can kind of extend it, but then that's opaque to anything that is not your code. But other than that, there's an extension point in how to write optimizers against it that'll rewrite things. And I forget the name of it. There's a way that you can effectively box a chunk of information to extend the logical plan as you want, and your system can manage that. Yeah, and then everything under the hood has an execution plan that needs to run. Execution plans are also a tree structure. Like, there is another method on the execution plan of the 19 that I have not shown that is get children. And so when you transform from one to the other, you're effectively going from this abstract representation of the structure of the query to a concrete executable that will be a tree of processing systems consuming streams of data up until the point at which you're returning one out the query end. And that's really what the executor is. The executor of this isn't some external VM or anything. It's really just Rust. It's your async runtime that is running this thing. And how the DataFusion framework structures it is each kind of separate line of execution in parallel, each sub-operation can pull on the data that is flowing into it and provide it upstream. And this whole thing is effectively pull. So at the end that is the query, like if you have a Postgres client calling into a Postgres fronted DataFusion-like database, then as you read rows, DataFusion will say, oh, okay, what else do I need to compute this row? And that'll propagate up the system. And that's where we get this diagram functionally. So this thing is the flow of kind of structure through this whole thing. You get your data phrasings. So you say, like, my table is a bunch of Parquet files stored on S3. You get your query system and semantics that you compile to a logical plan. The logical plan is this whole tree, including the table references. So it needs to know where it will eventually get that information downstream. A set of optimizations can run on that to like merge sorts together, deduplicate things, generally do all the optimizations you need to do before you translate that into an execution plan. And there's a whole set of interfaces for what it means to compile your logical plan into a physical plan, the execution plan trait here, which then can be optimized itself and eventually executed. And that execution includes a whole set of operations out of the box.
They also abstract the orientation aspect of it.
Yeah, so effectively, since it is using the Rust kind of Tokyo Streams API, That means that all of the operations are async operations that are shareable across threads. And under the hood, it is implicit how all of that parallelization works along the async task boundary.
I also noticed when you were writing out the code, you had cable scan in there and so on. How does this interact with indexes and so on?
So effectively, your execution plan is arbitrary code, and the index phrasings of things will have stages of pulling in index data and deciding how to transform the execution plan below it. And in the logical plan step, you could theoretically have something that is an index phrasing if you want, but really the indexes come in the execution plan layer.
Yeah, when you talk about tree and the execution plan, and it coming back up to be joined together, are the nodes on the tree running in parallel executions? Is there returning different parts?
Yeah, so you can think of Rust async tasks as coroutines. So what that means is each chunk of code doesn't actually know about whether it's running in parallel or being just kind of serialized and looking like it's concurrent, right? And that means that each piece doesn't have to care explicitly about the property of parallelism, but you can actually add more threads, and as it has the ability, it can spread the work out across all those threads. Does that answer the question?
A little bit, but also the tree part is already
Yeah.
connected still like that.
Hmm?
And then put back together.
Yeah, so if you imagine a set of, let's see here. If you imagine a set of these separate filter streams, so let's say we have 4 partitions that are each CSV files in our case, and we are filtering each CSV file for the records within some time range. Each of those can run in parallel. And we only need them together when we need to return the final set of things from this filter exec. And what that means is it kind of delays the necessity of that till the very end of the process. But because it's pull-based, we effectively, this operation says, hey, I need to start reading record batches, and it will block and be staged by the executor to then let all of these process those record batches first. And once those are all set as available, then it reschedules the filter exec to pull that data back in. And that'll happen at every join node in the tree. Is effectively you get a call and it'll say, I need to wait for the next record batch set to come to me, and it'll propagate all the way down. And because a record batch is a tunable size parameter, you can actually have pretty large chunks of work that are fully streamed on a single thread without having to have coordination, which allows for some pretty good performance dynamics.
Does this have any support for distributed execution across multiple teams?
So that's a great question, and the short answer is not internally, but you can, and I will show a version of this in a moment, you can have it such that you have multiple nodes that are all separate DataFusion instances, and you can do plan propagation where you do an optimizer pass that transforms it into the separate pushdown for those queries that then you distribute to the shards that then can return.
Let's jump in for a moment.
Sure.
We're actually working on this. There's a project called DataFusion Ray where someone will keep her data dump. His name is Rob Danley. He's actually doing some progress. Right? Anybody wants to help on the DataFusion channel, there's a DataFusion Ray on the Discord server. It's quite of a complicated issue, so we are.
So the comment was that there is a DataFusion kind of project building a DataFusion execution on top of Ray so that you can run DataFusion plans on kind of a Ray cluster. Ray is a kind of distributed execution framework. So that's all the things we need for a database. But we're still within one process. And this kind of reminds me of something. It looks a lot like SQLite, fundamentally. The shape of this, at least, right? It's columnar and a few other things. But fundamentally, SQLite is just an embeddable database. And why not use SQLite? And the short answer to that is that SQLite, since it is row-oriented, and since it is very optimized for this core embedding case, it's not extensible. It doesn't play nice with a lot of the kind of larger scale workloads we have. But if you only need a single node to do database stuff, just use SQLite. Don't use DataFusion. Unnecessary. So we're going to call our thing CSVQLite for purposes of comparison. And we have kind of a breakdown of where these things sit. So these are the various type names of the parser, compiler, logical plan execution, et cetera, that we've talked about. And here are kind of the equivalent pieces in the SQLite ecosystem. You'll notice there are fewer of them. And to some degree, the interface is simpler. So while you still have a file system interface, the SQLite format has everything in it. It's not just as simple as a CSV file. The SQLite bytecode execution framework, which when I share these slides, I would highly recommend you go read if you're curious. The SQLite bytecode VM is insane. It's very, very cool and has a lot of really nice properties to it. And then the query parser and compiler is all one step. It also doesn't differentiate between an execution plan and a logical plan. It just transforms on its underlying bytecode. And so everything is all very tightly coupled. And then let's see if I can actually get this demo. Woo! Okay, this is not as bright as I might want. Let me make it slightly bigger. Cool. So we have ourselves a binary that uses DataFusion with an exec command that takes a set of CSV flags and a query. And this query returns a nice big string. And what this is this is information about the fares in the New York yellow cab system from January of last year around this building. That is operating on, you can download files that are the yellow cab trip information. And we have a couple of these CSV files that we're just querying however we want. And we can modify this slightly, if the demo gods shine on me, to explain this, and that explanation, while a bit clustered, will actually demonstrate we have a logical plan, and each of these things are named by the base of what they're doing. So we have an aggregation, we have a table scan, and if you go down to the end here, we have a CSV exec, which is the thing that actually executes the CSV reads. And this is like the structure for DataFusion.
Kind of like the different instructions.
Yep,
in the
this is in fact the execution tree. This is the execution plan tree we are seeing visualized here. And because it is a linear operation of reads, it is a linear set of things. If you had multiple branching dynamics, which we will hopefully have in a minute, you will be able to see more. But that's kind of our like CSVQLite phrasing. Cool. All right, there's the demo. But most databases are servers, right? They're not just in some process. This would be useless if it was just a SQLite clone. Why would you just do that? So let's compare this to Postgres for a second, right? Like, what is Postgres doing under the hood? It really has something like this. It has its own little internal database engine that is running on a server somewhere, and then it has a wire protocol that you connect to it. So all we really need to do is slap the Postgres wire protocol on this to work, don't we? If we did that, then we have something like Postgres that does all of this. And here are kind of the comparisons of pieces, with the bolded bits being the difference between our CSVQLite phrasing and this, which I call cgresv. cgresv demo. So I have here running a similar binary, though this time it's running directly from Dazel, which has a serve command that takes a CSV and an address. And we are now serving. And instead of over here, same place we were before, let's use PSQL. And look, it connected. That's weird. We can run a command. Let's, in fact, not do the explain at the beginning first. We can run a command on this that gives us, this is a slightly different query. This is, in fact, the effectively daily gross domestic product of the yellow cab system around this building, and the average for every given fare, as well as the count of fares by day. And we can stick at the beginning of this the same explain, and this explain has a bunch of information attached to it. So we have our projection, which is effectively saying, like, these are the things we actually care about. We have our aggregations, which have a count, a sum, an average. Sub-projection on the underlying columns that we require to compute those things. We have a filter by the geolocations around this building. And then we have table scans, sort, more projection, etc. And at the end, we have ourselves this shiny little CSV exec, all available to us over the Postgres wire protocol. This is Postgres now, right? That's how this works. So that's cgresv. But aren't databases supposed to be cloud native? This isn't cloud, it's just one server. Shouldn't it horizontally scale and all of that? Yeah. My favorite example, old paper, but a good paper, is Bigtable. Bigtable didn't used to have a SQL frontend exactly, but now it does. And so it's a SQLite.
Well, you see, the SQL system generally. The core underlying query semantics are actually row filters. We can talk more about the insanity of that later. The storage system is level DB effectively, and it horizontally scales. It does a bunch of nice things. So here's kind of a big CSV, if you will, architecture diagram. You have a bunch of clients connecting to some central root node, some leader, and you have a set of tablet servers in Bigtable speak to some degree of cgresv instances. We're just taking a bunch of Postgres and making it our shards. So here's the shape of this, right? We don't really have shard coordination exactly.
We just kind of spit up a bunch of stuff you connect to it, but that's fine. Still using the Postgres wire protocol, still using DataFusion. Big CSV demo. All right. So now, instead of connecting to 5432, we're going to connect to 5555. And over here, you'll see that we have a bunch of existing instances running, these two and the one we started before, as well as this new command, which is here somewhere, federate. Federate, instead of taking CSV files like we've seen the last few times, takes shard addresses. And this address is a Postgres instance. It's a set of Postgres instances. So we'll run this thing. And you'll see these said something, someone connected to them. And we'll connect to this new place. And we'll run the same query we did before, and we'll get the same results we did before, except now it's running over more data, so I can actually go through more time. But if I add the explain on here, at the bottom, we'll actually see that it is making downstream SQL queries into underlying databases instead of doing CSV execs.
Is this the execution plan?
Yes, this is the execution plan. And so you'll see it's actually doing, these SQL queries are just selects. They have filter pushdown, which I actually implemented this morning because I'd forgotten it previously. And this will return kind of the union of all rows necessary to compute the rest of the query. And local to the leader node, it will compute the averages and such that are not commutative. Theoretically, you could also use, there's the DataFusion Federation project that's a bit experimental that I considered using but decided to be a little simpler for a demo here, that can repackage as an optimization pass more of the query to be performed on the shards so that you don't need to pull as much to the root.
So, and what does each shard one? Does it run just...
Each of these shards is the cgresv instance that we saw before. They're all just cgresv under the hood.
So it does run like a DataFusion kind of...
Yes, it is.
And then there's one DataFusion that kind of tells them, like, queries them individual.
Yep. So, serverless? What if we push all our CSV files to S3? That makes it serverless, right? That's how that works?
That would be, yes.
Well, I don't have a demo for that right now. So I could, after the talk, show you how that actually works. Like I can make it work, but I don't have it pre-canned. But that's kind of the core of everything. If you want to see more details on actual code, I'm giving a talk next week at the Rust NYC meetup where people expect more just raw Rust. And should be fun. I should have more demos there. That's it. Doing it?
Great. Start with Frank. Yeah, thanks to the talk. In the distributed sense, what does the catalog input look like to that lookup? Like, how do you describe the tree of sources?
Yeah, so in this particular structure, I have what are called table providers. And so a table provider in this phrasing, I wrote a custom table provider that is a union table provider. And what it does is it takes a set of table providers, in this case, the things that described the CSV retrievals earlier, and it then does a push down on the scans. So whenever it needs data, it'll say, hey, union table provider, provide me all the data for this query. And do you support this partitioning and these filters? And it will effectively take a union of all of its internal things and return those as requested from it.
So is each of those nodes own a shard, or is it just like a scattered together?
In this structure, for simplicity, each of those subtable providers owns a separate shard. You can be more complex. You can actually, like the DataFusion Federation structure is trying to be more intelligent about having an optimizer pass that can figure out what subset of the query might relate to a federated queryable thing and rewrite it so it can push down. And then you could theoretically have a table provider that talks about multiple shards, have it rewritten so it hands down to the things you mean.
It's just more code, right?
Just more code. It's super pluggable.
So, with LLVM, there's been a lot of just explosion of different languages because it's just much easier to implement them now. So what do you think will be the new kind of front ends that you see people build upon to make sure to repeat?
Yeah, so the question is with LLVM, it has made it a lot easier because you don't need to do all of the infrastructure to have new languages. And what do I see as kind of the new languages and things in this DataFusion ecosystem? And I would phrase my answer slightly differently than how the question is phrased, in that it's less about necessarily new query languages and more about what does this empower generally. And I think at a fundamental level, this means that databases don't need to be made by database engineers. You can actually have a normal infrastructure engineer who doesn't understand how query optimization works, but does understand their data and how it's consumed, be able to slap DataFusion on it and then kind of munge it so it works, right? I think a lot of my explanation for why we've seen so many more databases come online is that there are more kind of subtly different use cases that people need, and they don't see things on the market solving that the way they want, so they try to solve it themselves. And I think in reality, this kind of makes it so you don't need to do all the core bits. You can just make it oh, okay, I'm still using SQL, but now I have access to this truly esoteric, weird underlying format. Or hey, I want to write J, so I'm going to query Postgres with J because I translated an APL variant.
I want to write SQL across my 100 terabytes of XML file. I do that for a living.
The XML's great. I could give a whole talk about how great XML is.
Yeah, question back there.
So, you put checkouts faster over the slides.
That's a great question. So there are kind of two ways to answer this. I mean, there are more than that, but there are at least two ways to answer this. One of them is that the structure of Apache Arrow in memory and Tokyo for effective scheduling makes it so that a lot of the time an individual thread doesn't actually have to synchronize and can pull exactly the amount of data it needs without having to do a bunch of extra work. And so you end up with this pipelining that implicitly happens under the hood with how Rust streams are structured that makes it so that DataFusion is comparable. I mean, DuckDB is a morsel-driven style, fully integrated database system that is supposed to be super fast. And DataFusion is Volcano, right? It's old school database. It's not super intelligent. It's just slow in most modern database engineer researchers' phrasings, and yet it beats it a lot of the time. And I think a lot of that is the fact that because of how the Rust ecosystem it is built on has architected the underlying pieces, makes it so that that can actually execute quite quickly with a fairly straightforward phrasing. The other side of this is actually one that plays into the LLVM phrasing. One of the things that makes this fast is because it can get broad investment. Lots of different people can write optimizers, and those optimizers can be configured in open source without having to rewrite the whole underlying database And so now the comparison is like, do I write my whole vertically integrated database that is this way? Do I use something proprietary that someone else built? Or do I contribute a tiny bit open source on this thing that is exactly the optimizer that I'm missing? And so I think long-term, the fast comes from classic open source contribution, but in the immediate sense, from a general architecture and performance standpoint, it's about the async runtime and all those details.
I actually have a question based on that. You mentioned, and this is just me ignorance with Apache Arrow. You mentioned Apache Arrow is multi-language. Does that mean DataFusion is also implemented in multiple languages? I saw you doing Rust, obviously. I think it's because you like Rust.
So the short, like, the question is, Arrow's multiple languages, is DataFusion multiple languages? And there are kind of two sides to this. One is Arrow is kind of an abstract specification of memory layout and all those bits. And so you have different implementations of that so you can share across language boundaries, with each side being native to that language. DataFusion is not that. DataFusion is all written in Rust. But Rust has one of the best ecosystems for how to surface a Rust library into other languages. So you can run DataFusion from Python really trivially. In fact, IBIS has a DataFusion backend that you can just use, and it's great. IBIS is to compare to Polars and everything. Like if you use IBIS, you can just swap out what your backend is and see if Polars is faster.
The question is, how lightly is rate? Like, can you use it on the client side?
From a bytes standpoint, it needs a lot of bytes, some effort. So fundamentally, there's nothing that says this has to be bloated, but it is. And I have not yet looked into exactly why that is. I have suppositions that I will not put on the record, but at the moment, the base binary I'm using here is 60 meg, and it's not doing much more than just include DataFusion.
So you're not shoving that over the wire into a...
You're not compiling DataFusion to WebAssembly and shipping it everywhere anytime soon.
So I can send that reading is for suckers. Does DataFusion give me, if I want to write something, a traditional RDBMS guarantees or?
That's a great question, and one that we can talk about over beers. If you want to talk about what a CSV wall might look like, that's also another thing we can discuss.
Question was, how does writing work?
How does writing work? The short answer in general for batch workloads, so if you're doing transactional workloads, which I think was the implication of your question, it has the hooks to be able to build a system like that, but it is not designed for that first and foremost. If you're talking about writing out data that you've done as a result of a transform, if you say I digest data A and write it to location B, it has great Parquet writers and things like that allow you to do large scale batch workloads or even streaming workloads that you do partitioning on.
But insert statements are not necessarily the thing it's good at.
Insert statements are not what it is optimized for. But being an open project, you can contribute that, and maybe in 5 years it'll be incredible at it.
Yeah, I've heard that before.
Yes. Can you just clarify? You started out by saying that it's built on top of Parquet and columnar data, but then you're using CSD, which is these.
Sure.
So how? I just lost it.
Okay. So there are two pieces there. The question is I started talking about columnar data and all of the majesty that is Apache Arrow and all of this. And then I started using CSV as my underlying format, which is inherently row-oriented in a lot of ways. And to some degree, that was to demonstrate that it can read row-oriented data. But also, all of the in-memory stuff is still columnar in nature, and it can get some advantages for execution and compression, even though the underlying thing is reading a row-oriented format. There is an aside here that there's no reason you couldn't have a columnar CSV file and read it, and maybe next week we'll have some discussion of that at the Rust NYC talk.
So you're translating it, it's translating the...
Yeah, in as it is reading it, so the question...
The storage itself is stored columnar, you're feeding it CSV file, not stored natively.
So the question is is it translating this at... And in this case, it's translating it at runtime. So the CSV files, it's reading them. In this case, it's scanning the whole CSV file. If you wanted to compare this to Parquet, you could think of each CSV file as being a separate row group. And it reads all of it together and converts it into a set of record batches in Arrowland and all of this stuff. There's a crazy thought that I had that I did not have enough time for this talk of like, what if we faked parquet files with a bunch of CSVs in a tarball and we made it so we could do, it'd be great. Anyway.
But over here, do you mind going back to that slide where you were talking about actually everything? Pretty much S3. Skyries and the other servers. Okay, so I'm just trying to unpack the different layers of abstraction that could trace. So first there was the single node DataFusion. Yeah. And then you brought it up to using the federated extraction.
Yeah, we have kind of in process, we have server side, and we have federated.
Gotcha. So also just kind of thinking back to the different parts of the database that did. So in order to actually implement this, did you have to re-implement a new like logical planner and executor in order to?
Nope.
How did that work?
So because per the earlier question about like how on earth do I kind of surface these cgressvs to this DataFusion? So the question is effectively like, how did I generalize my single server planner to the federated planner, right? And the answer here is, from the perspective of the federated planner, each of these looks like each of the CSV files does to this server. So that federated planner understands that it needs to do a SQL query to retrieve data. But from its perspective, it looks the same as just reading a file. And so it doesn't need to do anything special. It just says, I have data over there. Let me get data from there. How do I do it? Well, let me generate the SQL to do so.
Okay.
Does that kind of answer the question?
Yeah, that roughly makes sense. Okay, so effectively, when you perform the query and you pass in federated with all of these data sources, that effectively was like a higher level plan of you telling the database engine where to fetch the data. And if you wanted this to be truly dynamic and variable, then you need to implement a system which chooses which shards to talk to and how to push down the variance to those shards.
Let's see, where is this slide? Yes. This slide is relevant in this context. So effectively at the beginning of the structure before the query actually gets constructed. So you could dynamically do this in the server. There's no reason you couldn't do this. But in order to build a logical plan, you need to know where your data is stored and the query. Both those things need to be known. And in the case of the federated circumstance, this is an extension that is another database, not a CSV file locally, and still SQL in most things. And so at that time, when it constructs the logical plan, at the leaves of the logical plan, it has 3 different databases that are separate reads.
But does know anything about the dimensions?
It has no idea about the dimensions. In fact, at that point, it doesn't even know what the fields are. Like this doesn't actually know, except dynamically defined via the queries, that this has that information, and that is constrained by how you configure the catalog in the first place.
Shard as context pops to different subsets of data.
Hmm?
There's no overlap.
Each shard, as defined in my very canned demo, has no overlap between the underlying data. If it did, you could have extra information about deduplication across the shard boundaries if you did smear the edges. Then you would have to, at the very least, have enough information to communicate the shard boundaries to the shards.
Do you offer an enterprise support plan for?
I mean, if you need some solutions that DataFusion might be good for, I'd be happy to talk with you.
How does that affect optimize that?
So in this case, and the question is, how does that affect the optimizer? In this case, because the shards are fully orthogonal, it has all the information it needs. It doesn't need any extra information, and it is doing filter pushdown. So it doesn't need to worry about optimizing each of the, it doesn't need to care about what the CSV files are on the remote node, because it is passing down its own separate query that is the subset of the retrieval that it needs. So it effectively can say, hey, give it, the one thing it isn't optimizing away is if this has none of the data, then it still has to make the request. But under the hood, this thing is delegated to for the fundamental pieces. That being said, you could have extra annotations in the execution plan or the logical plan that tell it what the bounds are, and it can early prune an optimization pass to say, I don't even need to retrieve things from these shards.
Like if this were blocked out by date, like this is,
Yeah, so
A, B,
exactly.
anyway, it should be March, and your query said March. It would make these queries anyway if it doesn't need to, unless you said, oh, this one only has March. I know what March is. I don't need to make this call.
You can have that information in the execution plan, and it can make that decision earlier on in the process. But in the case of how I wrote this, no, it has no idea.
Yours is just dumps a spread and check. And
It's a broadcast and union.
But it also matters filtering. What do you use that? What index you book to access first?
Sure. In this case, if indexes existed, those indexes would be at the shard layer. Not you could. Well, so it'll be a scan across all of the shards, but each of the shards individually doesn't necessarily have to read all of disk if it knows its local constraints.
For common applications of DataFusion, are secondary indexes common, or does it just typically scan everything?
So the question is, for common applications of DataFusion, are secondary indexes common, or does it normally scan everything? I have not had a ton of experience running DataFusion in production, so I can't strictly answer that. For like large scale analytics systems, secondary indexes often get really hairy and are a pain in the ass. And my experience talking with people is that they generally prefer not to do that. But I don't know when you do it, what the right structure would be.
let's do two more questions. Yeah, this one here. In your
Did you actually end up touching much of that Apache Arrow like code or bindings, or did you actually end up just only using the DataFusion strategy?
So for the purposes of this talk, and yes, I am just going to a very public repo that you all can look at if you want to. The question was, did I touch much, if any, of the Arrow code? And the short answer is no. This is the entirety of all of those demos. Oh, zoom in. This is the entirety of all of those demos. It is less than 400 lines of code. And the piece that actually does the union filter pushdown and everything is this table provider. This is a full implementation of the table provider. And here's the scan implementation. And all it does, right now it doesn't even check that the schemas are consistent for reasons. But it takes constructs a DataFusion official exec plan that is a union exec across subplans. And so all this does is it takes some set of table providers and it does the union over them. And it's correct because non-commutative operations are only done on the leader. If you push those down, it would not be correct for average. But for the purposes of this is perfectly fine as it runs. If you want to do more complex things, your table provider and other things get more complex. But that's all that's there. And like you'll notice, this doesn't even talk about any of the data passing across it. It just talks about generally the shape of how the query works and returns this execution plan. The execution plan is the thing that actually cares about the record batches. And up here you'll see the, let's see. So serve is all managed by the venerable PG wire crate, and the like local tables are all just some source listing. Why is this massive? There we go. So effectively this is a listing table. So a listing table is a DataFusion helper that lets you have a bunch of kind of underlying files and union them as one table, and then it can understand the pushdown for those things. And you can add extra constraints to do that as you want, and it just registers this table. And the same thing happens down in the Federation. It does a bit more work to kind of construct the shards, and there's some nasty types there. But at the end of the day, all it does is it takes that kind of union table I constructed and it registers it. And then behind the scenes, it has all the stuff written that does all of the things to plumb everything together. And technically, if I wanted to do the serverless thing, all of this supports arbitrary object store. If I had this off on S3, could totally do that, but I don't have the files on S3 right now. I have to like configure things. And,
in the Amazon crate sounds like a pain.
Don't even need to do that. The
It probably is.
The DataFusion project owns the object store crate for Rust, which is a generic object store crate across any provider, and it does all the work for you.
Maybe that's why it's 60 megabytes. Well, any more question? One last one, or are we gonna go to a bar? I think we're good. Thank you so much. That was great.